Hey everyone, welcome back to Math 261. This is Scott. Let's get started. On the agenda today is section 1.4, which is a continuation of section 1.3, which we looked at last time. So in section 1.3, we looked at the vector equation that was equivalent to the systems of linear equations that we saw in sections 1.1 and 1.2. And now what we are going to do is look at the matrix equation that also corresponds with these. So the matrix equation, and in particular, the form of the matrix equation that we're going to be discussing is AX equals B. And here the A is capital, the X and the B are vectors, so they have the little vector insignias. Alright, so first off, I should just note that it is the custom in this class and in most contexts to label matrices with capital letters, and then lowercase letters such as little a, little b, little x can stand for scalars or vectors, or the entries of matrices, but matrices are usually written with a capital letter with no extra mark. Now, first, let's discuss the very notation here. What we have written here is AX, as if there's a multiplication happening. How would a multiplication even happen between, on the one hand, a matrix, and on the other hand, a vector? So let's discuss that. So multiplying a matrix A by a vector X. Alright, so first off, let's imagine that A is made up of columns. We can call them like A1, and I'll do that to indicate that these are columns. A2, A3, up to A n. And let's say that X has entries x1 up to xn. Then, by definition, AX is going to equal then x1 times A1 plus x2 times A2 up to xn times an. These little lines above and below, those aren't ones, those are just me indicating that this is a column vector, it's oriented vertically, and it fills up the matrix. Technically, that would already be, it's a little bit redundant because these are already column vectors by the notation of the little arrow above, but just to be extra clear, a little hat on that. But just to be clear, I wanted to double down on the definition there and show that. So then, for example, let's suppose we had some numbers here. Let's suppose that we were talking about A is equal to 1, 2, 3, 4, 5, 6. And let's say that X equaled 7, 8, 9. So then, AX would equal then the first entry of x times the first column of A, so that's 7 times 1, 4, plus 8 times 2, 5, plus 9 times 3, 6, which then, if we actually apply these scalar multiplications, then we'd get 7, 28, plus 16, 40, plus 27, 54, and then we would add these up. So 7 plus 16 is 23, plus 27 is 50, and then 28 plus 40 is 68, plus 54, so that's going to be 100 and, so 68, so it's going to be 122, I believe. When in doubt, just check it. Don't be a hero. There is no shame in using technology to do some of the grunt work for us. And I just made sure, because I got a little nervous, that that maybe I'd made some mistake there. But sure enough, it adds up to 122. So that's all good. So notice here what happened. So the entries of x were put in correspondence with the columns of A. What that means is that matrix multiplication, for one thing, is only even defined if the number of columns of A matches the number of entries in X. So note, this multiplication is only defined if A has the same number of columns as X has rows. So in particular, here, what we can have is, for example, if A is m by n. So remember the notation, m by n, first comes rows, then comes columns. Then x must be n by 1. So in other words, in order to do the matrix multiplication, the inner dimensions have to match. So m by n times n by 1. So these must match. So we need the inner dimensions to match before this matrix multiplication to make sense. Now, before we go on to the implications of this matrix multiplication and what it has to do with both vector equations and systems of linear equations, I'm going to also give an alternate characterization of this multiplication, what your book calls the row vector rule for multiplication, and it goes like this. So the row the row vector rule for multiplying. And it looks like this. So the easiest way to see it is with the example, and we'll just do it with the same example as before so we can make sure that it comes out the same. So let's say that A is equal to 1, 2, 3, 4, 5, 6, and X equals 7, 8, 9. And what it does is it basically streamlines the process that we did here. So in the previous process, what we did was we distributed the entries of X to the different columns of the matrix, and then we did the scalar multiplications, and then we combined them. But here we could actually do that all more or less in one fell swoop by just doing 7 times 1 plus 8 times 2 plus 9 times 3. And then downstairs it's going to be 7 times 4 plus 8 times 5 plus 9 times 6. And then the numbers that we get are the same numbers we got when we were applying the other one. So we'll have 7 plus 16 plus 27 I mean. Upstairs we'll have 28 plus 40 plus 54 downstairs. And since these are the same numbers that we were adding last time, we should get the same results. And so we'll get 50 and 122. And what this basically amounts to doing is taking, for those of you who've been around the vector block a little bit, it amounts to taking the dot product of the column vector x with the row vectors of A. So this means basically we take the dot product of, products of the rows of A with the column vector x. And that's why this is called the row vector rule for multiplying, because it's treating the rows of A as a vector, which in turn are being multiplied in a dot product fashion with the column x. But this is just another way of doing it, and you can use whichever of the two methods you find most convenient for whatever purpose you are multiplying. Now let's try an example. So multiply, if possible. So here, let's try an example of a multiplication done by the row vector rule, if we can. So let's say what we have is let's say we have a 3 by 2 matrix. So let's say we have -1, 5, 7, 2, 2, 6. And we want to multiply that by the vector 5, 2, 1. Okay. Now, the row vector rule for multiplying is only an alternate way of writing what amounts to the same operation. And in fact, you see, it only took like one line of calculation before the very numbers ended up all being the same as what we got when we did it the other way. So the rules for multiplying are no different whichever way you do it. They're just two ways of looking at the same process. So this can only be possible if it would have been possible to do it by the other means as well. Now notice here we have 3 entries in this vector. We have only 2 columns in this one. This is a 3 by 2, and this is a 3 by 1, and these don't match. This is a mismatch. These are mismatched dimensions, which means that it is impossible. This is not defined. Okay. And that was, of course, highly implied by the very language of this example. Nobody ever says multiply if possible, unless there's a lurking possibility that one of your examples will prove impossible to do. Okay, so that one wasn't possible. But what if we just dropped that 1 and tried it again? So -1, 5, 7, 2, 2, 6. Now multiply it by 5, 2. Well, now what we'll have is 5 times -1, and here it doesn't say which method to use, but we ought to take our new method out for a test drive, see how it works out. So 5 times -1 plus 2 times 2, 5 times 5 plus 2 times 2, 5 times 7 plus 6 times 2. So this is what happens if we take each row and multiply it in dot product fashion with the column vector 5, 2, and that gives us -5 plus 4, 25 plus 4, 35 plus 12, and that's going to be -1, 29, and 47 by the look of it. So that's how the multiplication, just as an arithmetic matter, works out. Now, what this has to do with the stuff that we had been talking about before all comes down to the fact that we have now just expressed the matrix product as a product that combines columns of A with entries of the vector x, which is itself exactly in the same fashion as the vector version of the equation that that we were dealing with before. So here's a note. If A1 up through AN if these are all column vectors that form the columns of A, and x equals x1 down to xn. So in other words, if x is a column vector of unknowns, n unknowns, then the matrix equation AX equals B is equivalent to the vector equation, x1 a1 plus x2 a2 plus dot 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 up to the ends xn an equals b, which is also equivalent to the system of linear equations whose augmented coefficient matrix is, and then here we're just going to have the A1s, or the A's. Actually, I'm going to write this in the usual way that I wrote it before. So A1, A2, dot dot dot, AN, augmented by B. So what this is saying is these are just three ways of looking at what amounts to the exact same situation. So we can have it written as a matrix equation, AX equals B. We can think of it as a vector equation, which relates the weights, the unknown weights of known vectors. Or we can think of it as a system of equations, which we would often express in its augmented matrix form as such. Now, now what we can have is a theorem that relates the existence of solutions in all of these cases. The existence of solutions theorem is this. So AX equals B has a solution. If and only if, so it does have a solution if this is true, and it only has a solution if this is true, if B is a linear combination of the columns of A. In other words, if it's in the span of the columns of A. So to use the language from 1.3. Now, what that also means, so i.e., the system that corresponds is consistent. Now we already know what it takes for a system to be consistent. The system has to never end up with a row of all zeros followed by a non-zero entry. Now let's explore exactly what this means and doesn't mean by looking at two similar but contrasting examples. So they're both going to be asking the same thing in basically the same situation with just one slight important change. So the question is going to be, for what values of B1 and B2 do the following matrix equations have solutions. And here's how this is going to go. So example A, we're going to have a matrix A, which is going to be, let's say, 1, 2, 2, 1, x1, x2 is equal to B1, B2. So this is going to be example A, and then for example B, the change we're going to make is to this matrix right here. So now, let's have a look. Well, according to what we've said in that previous little theorem there, we've said that this matrix equation is fundamentally equivalent to the system of equations that involves the augmented coefficient matrix. It looks like this: 1, 2, 2, 1, B1, B2. Now, if this is the same thing, then we should look for what would make this characteristically consistent or inconsistent. And in particular, we would be looking for whether a row reduction of this will lead to something of the form 0, 0, non-zero. So that's what we're on the lookout for. So we row reduce this, trying to see if we can get this to be all zeros until that augmentation bar. So we row reduce away, and it looks like the first thing we would do is we would try to cancel out the 2 down there. So that means row 2 is going to be replaced by -2 times row 1 plus row 2. And that's going to give us 1, 2, B1. The first row is not being changed here, it's being used. And then we're going to have a 0. We're going to have -4, so it's going to make a -3. And then we're going to have a -2 B1 plus B2. And now if we were trying to continue here, we're already actually clearly not going to be able to do any more row reducing to get rid of this. And so we're not going to be able to eliminate this variable right here, which means that this will never have the form 0, 0, and then the augmentation. So here we're talking about this row. 0, 0, and then the augmentation, and then a b, where the b is not equal to 0, which means that all choices of b1 and b2 here are fair game. So this means this is always consistent. Which means that b1 and b2 can be anything. Okay. So that's what happened in that case. Now let's alter the case a little bit by changing the matrix that we had here. So instead of this little matrix, let's have a different little matrix. Let's have a matrix 1, 2, and then this side will be, let's actually make it 1, -2, and this one will be -1, +2. So this is another 2x2 matrix, not so different looking really from this one. So let's just see what happens. x1 and x2 are the variables, and then the question is what regulations do we have to put on the b1 and b2 here in order for this to end up being consistent. So last time it turned out b1 and b2 were completely open. They could be anything they wanted, and the system would never fail to be consistent. Will that be the case here? Let's find out. Well, first step, we just rewrite this in the matrix form, the augmented matrix form that peels off the coefficients and ignores the x's. So we have 1, -1, -2, 2, and then b1, b2 on the other side of the augmentation bar. We're going to row reduce this. So we're going to do a very similar thing here. We're going to try to cancel out the entry below the leading one there. And so we're going to take 2 times row 1, not this time it's going to be positive 2 times row 1, not negative, plus row 2, and that should take care of that. And let's see where this leads us. So 1, -1, b1, and then we're going to have a 0. We're going to have a 0, and sorry, there's a 2 down there. And over here we're going to have 2 times b1 plus b2. So now, all of a sudden, we are in the danger zone here. We don't have to go any further here. We can already see what it is it's going to take and what it is that would do us in here. So what we need, we need 2 times b1 plus b2 to not equal, I'm sorry, to equal 0. To equal 0 for this to be consistent. If it's not equal to 0, then that's the telltale sign of an inconsistent system. So in other words, we need b2 to equal -2b1. For consistency. So here, we did not have a free hand in the b1 and the b2. They are they're very tightly regulated, and in fact, once I know what b1 is, I can tell you immediately what b2 has to be, or vice versa. If I know what b2 is, I can immediately tell you what b1 has to be. So what that means is there's a very delicate tightrope you have to walk if you want to stay consistent in this case. Here, however, there was no danger because it was not at risk of hitting the form that was a telltale sign of inconsistency. So never have this form up here. but it will have the form down here if we're not careful. So it only has a solution if the b's have a certain form. Now, what made the difference? What made the b's in the one case contingent versus the b's being completely independent? Well, if you look at the results of the row reduction here, row reducing in the one case led to an indication of a pivot in every row here. Whereas here, we cleared things out and got a row of all zeros. And it turns out that was that's the key make or break condition in this case. Okay, now let's try to connect this all and see what it is we can say about the relationship between matrices, vectors, and so on. So here's the theorem. So your book calls it Theorem 4, but there's no reason for us to necessarily do that. We are not going to go around appealing to this theorem or that theorem as though we are lawyers. We just need to know what the facts are so that we can be on the right side of the truth. Okay, so here's the setup. A is an M by N matrix. So, i.e., A has n columns each of which is an M dimensional column vector. So in other words, belonging to Rm. So Rm, remember from section 1.3, represents column vectors where each of the vectors have m entries, so m rows. So A has m rows, which means that each of its n columns has m entries. All right, then the following are equivalent. Now what that means is we're saying in this case logically equivalent, which means they are all true together or all false together, i.e. all true together or all false together. So they stand together or they fall together. So here are 4 statements, each of which is completely equivalent to each of the others. So for any B in Rm, so any m-dimensional column vector, Ax equals B has a solution. So that's that's the first of the 4 conditions. So in other words, we're saying no matter what B you choose, there's a solution here. So in the previous example, that would be like the first, not the second. So we're in the world of example A here. Any B could have been chosen, and this would have a solution. But let's think about what else that means. Well, what that means is there is a way to find the values of x that will make this, that we can use as the weights of the columns of A to make them equal B, which literally is saying there is a linear combination of the columns of A that will equal B. So for any B belonging to the world of m-dimensional vectors, so for any B in Rm, B is a linear combination of the columns of A. But wait, what that literally means then is that B is in the span of the columns of A. But B was anything. So that means all vectors in Rm are in the span. So span, remember, from section 1.3, is the collection of things that you can make out of linear combinations, are in the span of the columns of A. So another way of wording this, so in other words, the columns of A span Rm. So that's another way of wording it. So you would say they are all in the span of it, or the columns of A collectively span Rm. But because of what we just saw in the previous example, in order for this to be true, so these three things are all just restating the same fact, but what does it take for those to be true? Well, let's look back at our example. What did it take? It took never being able to get a row of zeros when you row reduced, which meant that we need there to always be a pivot in every column of A. We can't row reduce it down to all zeros. So these three things are all just rewording the same fact. And now D is where we really get some new info on the matter. D connects it to an unexpected fact, and that is that there is a pivot in every row of A. So this is as in example A above. So these three facts are all just different ways of wording the same thing. And this is what we discovered with our pair of examples above. What it takes for these things to all be true is that we need to not be able to get a row of zeros followed by a non-zero when we row reduce. So there has to be a pivot available for every row of A. All right, so this was an exercise in applying our new language and notation and terminology. So this was an extravagant demonstration of some new and alien ways of wording things and thinking about things. But But essentially, what we are coming to the conclusion, the conclusion we're coming to is that everything is basically a different way of looking at the same fundamental relations that we could be dealing with. So that is systems of equations, vector equations, matrix equations. These are all different versions of the same underlying reality, and that's what this class is here to explore. So join me next time for the next episode of Math 261, where we will continue exploring these very interrelated yet very very strange seeming topics. Until then, bye.